Good afternoon, everyone. My name is Chris Ogren. I'm a graduate student at the University of Michigan. I work with Professor Igor Yovanovich in his research group, and today I'm going to take some time to discuss some of my recent work on the development of calibration sources for a large gadolinium-doped water shrink-off detector. Before I begin, just a little bit about the group that I perform this work with. I am a part of the Watchman AIT collaboration. It is a large group collaboration that includes over 140 people across 26 different institutions all over the United States, including universities and national labs, as well as United Kingdom, England, and Scotland. And it spans over 10 different time zones between the University of Hawaii and some of the groups in England on GMT. So you can imagine it is a little bit difficult scheduling those Zoom meetings for the all hands collaboration group meetings. So just to get started with a little bit of motivation, the focus of my work is on measuring antineutrino signals, and the reason we're interested in that is because antineutrino signals can be used for the remote monitoring of nuclear reactors, right? Fission reactions happening in nuclear reactors release copious amounts of antineutrinos, and those antineutrinos being weakly interacting particles, they're a signal that cannot be shielded, and they can also be detected at long standoff distances, up to 10 to hundreds of kilometers, depending on the intensity of the signal and 1 over r squared. And the way that we can use these signals for a couple of different applications relating to nuclear reactors, one of which would be monitoring the operation of known nuclear reactors. So you could tell, if one reactor core was, on or off, being turned on or turned off, being operated at less than full burnup, which might be associated with some sort of characteristics you would look for with, diversion of material or production of plutonium, for example. And additionally, you could use these antineutrinos for the discovery of maybe undeclared nuclear reactor activities. This work is relevant to the NNSA mission. Remote reactor monitoring via antineutrino detection supports the NNSA nonproliferation goals by enabling a verification method for declared reactor sites and operational schedules, for giving a method for the discovery of undeclared reactor sites, and by giving an indication of departure from the declared operational characteristics of a reactor. For example, undeclared shutdowns to remove or repurpose partially spent fuel. So large water shrink-off detectors are a promising potential technology that could be used to carry out this detection of these remote antineutrino signals. The principal method through which antineutrinos are typically detected is inverse beta decay, in which the antineutrino interacts with a proton, typically in the large amount of water that would be inside the detector, which then produces a positron and a neutron. Now, in the detector design that's under consideration by the Watchman collaboration, this design uses this gadolinium-doped water. So when an inverse beta decay event happens in the water, you get Cherenkov light produced by the recoiling positron from the IBD interaction, and also that neutron is then captured by gadolinium-157 or 155 isotopes that are dissolved in the water. And when that capture occurs on gadolinium, that gadolinium has a very high capture cross-section and then releases the energy in the form of a high-energy gamma ray cascade, and those gamma rays then go on to interact with other electrons in the rest of the water volume, which then produce additional flash of Cherenkov light associated with that capture. And for the Watchman design, the detector is on the kiloton scale, and using that large volume is done to account for the low cross-section and the long distance 1 over r squared attenuation of the antineutrino signal. And also, the idea is for this detector to be built and placed in an underground mine, which will provide some shielding from cosmic radiation and reduce the background from other sources. So part of the deal with using these highly sensitive gadolinium-doped water shrink-off detectors is that they're a bit of a challenge in terms of calibration. And so there's a number of different calibration sources that are being considered in order to provide the reference points that are needed. Especially of concern is the gamma ray cascade that happens after the neutron capture on gadolinium. And that cascade has kind of a wide energy continuum spanning from a few MeV up to 6, 7, 8 MeV at the high end in terms of the total energy that can be released. So there's a number of sources that are being considered, and one of those sources, which is particularly of interest, is nitrogen-16, which provides a useful reference line near the high end of the gadolinium capture cascade. And some simulations and modeling that's been done by the Watchman collaboration so far has shown that by including this nitrogen-16 line, we can greatly reduce the statistical uncertainty associated with the energy calibration, as well as with the event reconstruction in the volume of this large water Cherenkov detector. So this is kind of an important calibration source. And then additionally, some of the other sources that have been proposed are thallium-208 and americium beryllium, which give additional gamma ray lines at about 2 and about 4.4 MeV. And then also some neutron-based calibration sources that can help give an idea of the detector response to those neutron captures on gadolinium. So americium beryllium also gives neutrons. And then there's some other potential sources that we are thinking of developing, such as maybe nitrogen-17 delayed neutron precursor, or americium on carbon-13, which is a neutron emitter as well. So speaking about that nitrogen-16 source in particular, one of the tricky things about nitrogen-16 is that it has a short half-life of about 7 seconds. So there needs to be a delivery system that can both produce the nitrogen-16 and then deliver it into the large detector volume before it decays away, so that you can get those decays occurring actually in the detector volume. So the design that's currently being considered is based on one that was successful for the Sudbury Neutrino Observatory, which utilizes a DT neutron generator and a gas target chamber volume around the generator, in which a CO2 target is used to produce nitrogen-16 via the NP reaction. And then that nitrogen-16 is built up in the gas, and the gas is piped into a smaller decay chamber, which is in which the decays take place and the the calibration source is delivered into the volume of the detector. Now, one thing that's interesting about nitrogen-16 is that it's a correlated beta gamma radiation source. So you have the beta particle that can be used as a time tag for when that gamma ray is emitted into the larger detector volume. And this is kind of a point of collaboration between our work here at the University of Michigan and with our partners at the University of Sheffield in the UK in terms of the design and development of this source. A little bit more details about that. At Sheffield, they're working on putting together the actual prototyping of the source delivery system and testing the decay chamber designs. They have a water tank that they can use once they build the system to then test how that everything works out in the water tank. And then at University of Michigan, we're focusing more on source generation. We have the DT neutron generator available to us, so we can do production tests as well as characterization of the radiation that comes from those sources, and in terms of the detector response to that. So just some examples of some of the work that we've done so far at the University of Michigan. Here you can see we've done some simple tests with nitrogen-16 production and then simulation and modeling. So we've done some quick experiments with our DT generator and water and CO2 targets. And then we use a large sodium iodide detector to measure the gamma rays that come out from that nitrogen-16 that we produce. And so on the left here you can see kind of the raw energy spectrum that comes from that nitrogen-16 after being irradiated with the DT generator. You can see the 6.1 MeV gamma ray triple feature there, photopeak, single, and double escape, as well as the 7.1 MeV feature, which is from the secondary decay mode of nitrogen-16. And then on the right-hand side, you can see we measured the time profile for the events in that 6.1 MeV feature range, and you can see that they conform fairly well with the expected exponential shape associated with the known decay constant for nitrogen-16. And then we've also built some simulation models of these large sodium iodide detectors, and we were able to get fairly close agreement between the detector response to 6.1 MeV gamma rays and what we measure experimentally in the lab. And then just a quick note, the difference that you see here is due to the fact that the only thing that was modeled was the 6.1 MeV gamma rays, and the other lower energy activation lines were not included in that simulation. So in addition to nitrogen-16, another alternative possible source of 6.1 MeV gamma rays that we're interested in, because it doesn't require an external neutron source to create, would potentially be americium carbon-13. Now, with americium-241, the high-energy alpha particles that are above about 5 MeV can leave oxygen-16 in its excited state following the carbon-13 alpha-N reaction, which can also emit that 6.1 MeV gamma ray that you can reach through the nitrogen-16 decay. So the idea here is to use a thin layer of americium-241 to minimize the energy losses of the escaping alphas, and a thin layer of, as pure as possible, carbon-13, because if you have more than maybe 1 or 2 microns of this carbon-13, then the alphas lose enough energy traveling through it that they no longer have a chance to produce the excited state of oxygen-16. And then we would use maybe a copper substrate, which is something that's not easily activated by the alpha particles and the energy of americium-241. And so we've done some simulations that suggest that a 1 millicurie americium-241 source could potentially produce on the order of 10 to 100 gamma rays per second at that 6.1 MeV energy, which again, this is interesting because if we're not able to use a DT generator for reasons of expense or for radiation shielding or other reasons, then this might be an alternative source of getting that calibration line. In addition to nitrogen-16 and these high energy gamma rays, nitrogen-17 is a possible calibration source that we're considering. The advantage of nitrogen-17 is that it can be developed alongside nitrogen-16 because they can both be produced using the same mechanism, which is NP reactions from the DT generator. The only change required being swapping out the target material, for example CO2, for something that's been enriched with the isotope oxygen-17 instead of oxygen-16. And the goal that we have here is to kind of demonstrate a proof of concept using some oxygen-17 enriched water target, and then show that we can produce this nitrogen-17 and potentially use it as a calibration source. And the reason it might be interesting is because just like nitrogen-16, it is beta-correlated radiation. In this case, it's a beta-correlated delayed neutron. So nitrogen-17 could potentially be a time-taggable source of lower energy neutrons with a discrete energy spectrum. Nitrogen-17 might be something that's complementary in terms of the current neutron calibration design. So for example, americium beryllium is what's currently been proposed, and nitrogen-17 would have a different design in terms of the tagging detector, target or decay chamber that would be used, which might offer different systematics in terms of using these sources in the ultimate large water Cherenkov detector. And what I mean by that systematics is in the amount of false tagging that, or false tag events that you get. For example, with americium beryllium, you can have a neutron that exits the source and is captured in the water, and a gamma ray could go back into that detector. You need a larger inorganic detector in order to use that 4.4 MeV gamma ray from americium beryllium as a time tag. So you have a higher chance of getting one of the gadolinium capture cascade gamma rays going and tripping that detector. And then if you don't ultimately get a flash in the PMTs of the larger water detector, that leads to a false tag. And because of the different geometry and the different mechanism for nitrogen-17, it would have some different systematics, so they could potentially be used as an alternative calibration and a cross-check against the other neutron sources that have been proposed. So just something that we've been doing so far. We've done a few production tests on making nitrogen-17 in our lab at University of Michigan. We've done it with our DT neutron generator and a small 2-gram sample of oxygen-17 enriched water. And we recorded the delayed neutron signal from nitrogen-17 during the times in between generator on cycles, using some custom-built capture-gated neutron composite detectors that we have. And you can see here on the right-hand side, this is a pulse-shape parameter distribution for these composite detectors, and the highlighted red region is associated with neutron captures, And so we think that's a pretty good indication that we're seeing some neutron captures in the delay time after the generator's been turned off, when these nitrogen-17 delayed neutrons should be being emitted. So to take this one step further, one thing that we're working on is a specially designed beta tagging detector that can be used to pick up that correlated signal, kind of analogous to the decay chamber that I mentioned earlier with nitrogen-16. This gives us a chance to detect that beta emission, giving us the time tag for both the gamma rays for nitrogen-16 and for the neutrons emitted by nitrogen-17. And so the idea of this detector is to enclose the target with as high of a solid angle coverage as possible with thin plastic scintillators that are good for beta detection but are small enough to reject most of the gamma ray background just because the form factor of interaction is low. It's supported by an oxygen-free housing that can be used in the DT neutron flux. That way, the reason that it needs to be oxygen-free is so that it's not easily activated to produce the isotopes and beta sources that we're already trying to produce in the target. So we get kind of interference from activation in the housing of the detector itself. And the shape of it is made to kind of couple the scintillators to the PMT. And there's also a removable cap that allows us to place the targets inside and remove them as we want to test different things. And so we were able to build this detector and conduct a few preliminary tests with it. You can see on the right-hand side, we placed some strontium-90 and thallium-204 beta-emitting sources inside it, and you can see the results that we get are in line with what we expect in terms of the beta spectrum. And the next step for this detector is to now take our enriched water sample and place it inside, and then use that to measure the correlated signal with nitrogen-17. So just to conclude, what we've accomplished so far is demonstration of production of nitrogen-16 and measurement of 6.1 MeV gamma rays. Americium-241 on carbon-13 might provide an alternative source of these 6.1 MeV gamma rays that would not need an external neutron source. We've also worked on nitrogen-17 as a possible calibration source that can be developed using the same delivery system as nitrogen-16, and nitrogen-17 might be interesting as a complement to the other neutron sources such as americium beryllium by providing a different neutron energy spectrum as well as different tagging systematics. And we've conducted some test measurements that appear to show nitrogen-17 production and the detection of delayed neutrons from it. And our next step is to measure the beta correlated signal from nitrogen-17 using our tagging detector that we've recently developed. So with that, I would like to take a moment to thank our sponsors, and I'll open it up for any questions. Thank you.